In the closing decades of the 19th century, the world of physics seemed almost complete. The giants of science had laid out the grand structure of classical mechanics, thermodynamics, and electromagnetism, and most scholars believed that all that remained was to refine measurements and polish details. To many, the mysteries of the universe were essentially solved. Into this world was born a young German student named Max Planck, whose path was not the glamorous tale of someone destined from the start to change the foundations of science, but rather the story of a man who valued discipline, persistence, and duty above all else. His early life and career were defined not by recognition or immediate breakthroughs, but by struggle, doubt, and a relentless devotion to truth, which would one day lead him to become the father of quantum theory. Max Carl Ernst Ludwig Planck was born on April 23, 1858, in the city of Kiel, Germany, into a family of scholars and teachers. His father, Johann Julius Wilhelm Planck, was a professor of law, and his mother, Emma Patzig, came from a family deeply rooted in tradition. The young Max grew up in a home where education and intellectual conversation were a part of daily life, yet no one suspected that this quiet, disciplined boy would later revolutionize science. He was not the type of child who craved the limelight or demanded attention. Instead, he carried with him an air of seriousness, a reflective mind, and a sense of order that would remain throughout his life. From an early age, Planck showed remarkable intelligence, but he was not regarded as a prodigy in the dramatic sense. He studied music, languages, and history, excelling in multiple fields, and for a time he even considered becoming a professional musician. Music was, for Planck, a lifelong passion, one that shaped his sense of harmony and order in the universe. Yet, when he turned his attention to science, he was captivated by the logic and precision of physics. It was a subject that demanded rigor, but also offered glimpses into the deep structure of nature. At the age of 16, he entered the University of Munich, where he quickly encountered the stern realities of scientific study. The atmosphere at Munich was not particularly welcoming to a young dreamer. One of Planck's professors, Philipp von Jolly, famously warned him that physics was a field where almost everything is already discovered, and all that remains is to fill in a few holes. For many students, such a statement would have been enough to drive them away to a more promising discipline. But for Planck, it was not the promise of glory that drew him to science, but rather the pursuit of truth. He did not enter physics with the expectation of uncovering great revolutions. Instead, he devoted himself with quiet determination to exploring its existing structure. This mindset, born of humility and persistence, would become one of his defining traits and one of the reasons he was later able to embrace radical ideas when no one else dared. Planck's early years as a physicist were not easy. He studied the principles of thermodynamics, a field still developing at the time, and he was particularly drawn to the concept of entropy. While many physicists treated entropy as a purely mathematical abstraction, Planck approached it with a philosophical depth, asking what it truly revealed about the laws of nature. He became fascinated with the idea that behind the apparent chaos of the world lay hidden principles of order. Yet, his investigations were not greeted with much enthusiasm. His first published works attracted little attention, and he struggled to find recognition among his peers. Despite the lack of encouragement, Planck persevered. He completed his doctorate in 1879 at the age of 21, writing a thesis on the second law of thermodynamics. This was no easy task. The subject was deeply challenging, involving abstract concepts that many physicists avoided. Yet Planck pursued it with patience, convinced that the law of entropy held the key to understanding the universe. In his early research, he was less interested in chasing fashionable topics than in digging deeply into principles that others overlooked. This choice, while not glamorous, was an expression of his persistence and intellectual honesty. He did not seek the approval of the scientific community so much as he sought to understand nature in its truest form. After completing his doctorate, Planck faced the uncertain career path of a young academic. teaching positions were scarce, and recognition was minimal. For years, he worked with little acclaim, often overshadowed by more prominent figures of the time. His lectures attracted only modest audiences, and his papers rarely stirred discussion. Yet, through all this, he continued his work with diligence, believing that science was a lifelong commitment, not a pursuit of quick fame. He married Mary Merck in 1887, and together they raised a family, which became a source of stability in his life even as his professional recognition remained limited. It was during this period that Planck developed a personal philosophy that shaped his scientific outlook. To him, the laws of nature were not arbitrary, but rooted in a deep moral and rational order. He believed in truth as an absolute, something that existed beyond human opinion or convenience. This worldview gave him the strength to persist when others might have abandoned the struggle. While many of his contemporaries were swept up in the excitement of new discoveries in electromagnetism and atomic theory, Planck remained focused on the fundamental laws of thermodynamics. His sense of discipline, shaped by both his upbringing and his own character, made him unshakable in his commitment to careful, precise research. The turning point of his career did not come from seeking out radical new ideas, but from a practical problem that many physicists considered unsolvable. By the late 19th century, scientists had been puzzled by the behavior of radiation emitted by heated objects, a problem known as blackbody radiation. Experiments showed that classical physics predicted absurd results, suggesting that objects should emit infinite energy at short wavelengths, something obviously impossible. This puzzle frustrated the scientific community, but it did not attract much attention, as most believed it was a technical problem that would eventually be resolved. Planck, however, saw in it a deeper challenge. To him, the issue was not merely experimental, but touched on the very foundations of thermodynamics and energy. Even before he arrived at his revolutionary idea in 1900, Planck's approach to this problem revealed his persistence and intellectual courage. He spent years attempting to reconcile the equations of thermodynamics with the behavior of radiation, testing one approach after another, often facing failure. Unlike other scientists, he did not abandon the problem when it became too difficult. His belief in an ordered universe, governed by rational laws, gave him the strength to continue searching for a solution. In these years, his struggle was immense. His calculations were painstaking, his progress slow, and recognition remained elusive. Yet, step by step, his determination pushed him closer to the brink of discovery. Planck's early struggles were not merely scientific, but also personal. His life was marked by hardships that tested his character in ways few could endure. He faced family tragedies, including the loss of loved ones, and later endured the turmoil of 2 world wars that tore through Germany. These experiences left deep scars, but they also forged in him a resilience that mirrored his scientific persistence. Even in times of despair, he continued his work, convinced that science was a path toward truth and meaning in a chaotic world. By the time he finally proposed the idea of energy quanta in 1900, Planck was not a young, ambitious researcher seeking fame, but a middle-aged scientist shaped by years of struggle, perseverance, and philosophical reflection. His discovery did not emerge from sudden inspiration, but from a lifetime of persistence in the face of neglect and difficulty. The quiet, determined student who had been told that physics was a finished field had, through sheer dedication, uncovered a principle that would transform it forever. Part of what makes Planck's early story so powerful is that it reveals how science is often advanced not by those who chase glory, but by those who are willing to endure struggle, to work in obscurity, and to remain faithful to their pursuit of truth, even when the world offers little encouragement. His early struggles were not wasted years. They were the very foundation of the character and discipline that enabled him to embrace an idea so radical that it reshaped the universe of physics. Without his persistence, without his willingness to labor in silence, the revolution of quantum theory might never have begun. Max Planck's path toward becoming one of the greatest physicists in history was far from straightforward, and the second half of his early journey reveals how persistence was not only a matter of scientific focus, but also a matter of personal endurance. The story of Planck before his great breakthrough is as much about character as it is about equations, for he lived through disappointments, skepticism, and hardships that might have silenced a weaker spirit. His ultimate transformation of physics was not the result of sudden genius alone, but the culmination of decades of steady effort against an unwelcoming tide. In the academic world of late 19th century Germany, physics was dominated by towering figures and fashionable theories. Students and researchers often clustered around the most celebrated scientists, drawn into the excitement of electromagnetism after James Clerk Maxwell's great unification, or the experimental achievements that were reshaping the laboratory. Planck, however, did not belong to these circles of prestige. His work in thermodynamics, subtle and abstract, seemed distant from the thrilling discoveries that caught the world's attention. In fact, his very choice of topic set him apart. Few young physicists wanted to wrestle with entropy or the abstract laws of energy distribution. Planck's persistence in this unglamorous field reveals the depth of his character. He was not chasing fame or following trends, but pursuing what he believed to be fundamental truths, even if the world was not listening. The challenges he faced were not only intellectual, but institutional. When he sought an academic career, he encountered a system that valued conformity and reputation. His earliest publications were read by few and praised by fewer. University committees regarded him with skepticism, and he often struggled to find positions that matched his talent. At one point, Planck feared he might never secure a stable career in physics at all. It was only after long waiting and repeated demonstrations of his reliability as a teacher that he earned appointments in Kiel and later in Berlin. Even then, he was far from a celebrated figure. His classrooms were not filled with eager disciples, and his research was not quoted widely in journals. Yet he pressed on, treating each lecture and each calculation with the same care, convinced that the value of science lay in its truth, not in its popularity. This persistence was not blind stubbornness, but a conscious philosophy. Planck believed in duty, in the sense that a scientist's role was to serve truth, regardless of whether the world rewarded it. He was deeply influenced by the German tradition of discipline and moral seriousness, qualities that permeated his upbringing. To Planck, the pursuit of knowledge was almost sacred, a calling that required patience and humility. This philosophy sustained him during years when recognition seemed distant. While others abandoned problems that did not yield quick results, Planck remained faithful to them, convinced that the laws of nature could not be arbitrary and that clarity would eventually emerge. One of the defining features of his struggle was the Blackbody problem, which haunted him through the 1890s. The issue was deceptively simple: how to describe the distribution of energy emitted by a heated object. Experiments had shown precise curves of radiation at different temperatures, but classical physics could not reproduce them. At short wavelengths, the predictions of established theory soared toward infinity, an absurd result. Many dismissed the problem as a quirk of mathematics or experimental error, but Planck sensed that something deeper was at stake. He devoted himself tirelessly to the problem, often spending sleepless nights with calculations, chasing an answer that eluded him year after year. It is important to understand the psychological weight of this struggle. Planck was not a young man bursting into the field with bold new ideas. By the time he wrestled with blackbody radiation, he was in his 40s, a seasoned professor with a reputation for reliability, but not for groundbreaking discoveries. For him to challenge established physics was not an act of youthful rebellion, but a slow, reluctant realization born from necessity. He wanted desperately to preserve the harmony of classical physics, to fit the problem into the framework he had studied so faithfully. But reality would not bend to his wishes. Again and again his calculations broke down, until he was forced to accept that something fundamental had to change. His persistence here was not only in working on the problem, but in allowing himself to follow truth, even when it contradicted his own beliefs. The journey was made heavier by the burdens of personal life. Planck's family was his anchor, but he was no stranger to tragedy. He lost his first wife, Marie, to illness, and later endured the heartbreaking deaths of his children. These sorrows struck him deeply, yet he continued to work, drawing strength from his conviction that science offered a kind of permanence beyond human suffering. He once wrote that truth is eternal, existing beyond the frailties of individual lives. In this belief, he found the courage to persist. The resilience that carried him through personal loss was the same resilience that allowed him to persist with scientific problems that seemed hopeless. By 1900, after years of frustration, Planck made the leap that would define his legacy. In order to fit experimental data, he assumed that energy could not be absorbed or emitted continuously, but only in discrete packets. This was not a conclusion he embraced lightly. In fact, Planck himself admitted that he introduced the idea of quanta almost against his will, as a desperate measure to make the mathematics work. Yet the very fact that he was willing to take such a radical step speaks volumes about his persistence. For years, he had clung to classical physics, trying to make it suffice. When it failed, he did not walk away in defeat, but pushed further, willing to risk even his most cherished assumptions in order to remain faithful to truth. It is easy, looking back, to view this as a moment of triumph. But at the time, Planck's idea was not greeted with celebration. Many scientists dismissed it as a mere mathematical trick, an artificial device to fit data, not a real description of nature. Planck himself was uneasy about it, struggling for years to interpret what it meant physically. The persistence he had shown in reaching the discovery now had to be applied again as he defended and refined an idea that few understood or accepted. Once more, he faced neglect and skepticism, but by now his years of struggle had prepared him for such resistance. He was not discouraged, for he had long ago learned that truth often reveals itself slowly. What makes Planck's story remarkable is that his persistence was not driven by the expectation of revolution. Unlike many figures in history who sought to break with tradition, Planck was, in temperament, a conservative. He respected the great structure of classical physics and would have been content to work within its walls. Yet his persistence in following the problem of blackbody radiation, no matter how uncomfortable it became, pushed him beyond those walls. He did not set out to transform physics forever, but his devotion to solving one problem honestly forced him into a discovery that changed everything. This is perhaps the deepest lesson of his story, that persistence in the search for truth can lead us to places we never imagined, even when we resist them. As the years went on, Planck's idea became the seed of quantum theory, expanded by Einstein, Bohr, and many others. His persistence had opened a door that others would walk through to build the strange, beautiful, and bewildering world of modern physics. Yet even as his fame grew and honors were heaped upon him, Planck remained the same humble, disciplined man. He never boasted of his role as a revolutionary, and he often emphasized that he had stumbled into quantum theory reluctantly. But those who knew him understood that it was precisely his character, his patience, his endurance, his refusal to abandon the pursuit of truth, that made the discovery possible. When we consider Max Planck's early struggles, we see a story that speaks to more than just science. It is the story of persistence in the face of neglect, of staying faithful to one's duty even when rewards seem absent, of bearing personal grief without surrendering to despair. It is the story of how a man who never sought glory nonetheless changed the world because he refused to give up. The Planck who entered physics as a quiet, serious student, warned that there was nothing new to discover, became the man who proved that the greatest revolutions come not from chasing recognition, but from serving truth. His legacy reminds us that the struggles of the early years are not wasted. Every unnoticed paper, every ignored lecture, every calculation that ended in failure. All of these were not dead ends but steps on the path to discovery. They were the crucible in which persistence was forged, shaping a character strong enough to accept radical truth when it finally appeared. In the end, Planck's early struggles were not the background to his success, they were the very essence of it. Thus, the story of Max Planck's persistence is not only a chapter in the history of physics, but a lesson in human resilience. It tells us that great change is often born not from brilliance alone, but from the quiet, steady determination to seek truth despite all obstacles. And it shows that even in a world where everything seems discovered, where doors appear closed, persistence can uncover new realities that transform our understanding forever. At the dawn of the 20th century, physics appeared to stand as a completed cathedral of knowledge. For more than 2 centuries, the principles laid down by Newton, refined by the laws of thermodynamics, and crowned by Maxwell's elegant equations of electromagnetism, had created a vision of the universe that seemed whole. The world appeared like a vast machine, governed by deterministic laws that left no room for uncertainty. Scientists boasted that all that remained was to measure constants more precisely, to refine equations already known. Yet hidden within this confidence lay cracks, small puzzles that classical physics could not solve. Among these was the mystery of blackbody radiation, an apparently technical problem that would become the gateway to a revolution. Out of this problem emerged the quantum, the most disruptive concept in the history of physics, and at its center stood a man who did not seek upheaval, but only truth, Max Planck. To understand the significance of what happened in 1900, we must first picture the problem that had confounded physicists for decades. When an object is heated, it glows. First red, then orange, then white as the temperature rises. This glow, known as thermal or blackbody radiation, seemed simple enough, yet the precise pattern of the emitted light defied explanation. Experiments showed that the energy emitted at different wavelengths followed a particular curve. At long wavelengths, energy increased steadily, peaked at a certain point, then fell off at shorter wavelengths. Classical physics, however, predicted something entirely different. According to the Rayleigh-Jeans law, as wavelengths became shorter, the energy radiated should grow without limit, climbing toward infinity. This absurd prediction became known as the ultraviolet catastrophe. Clearly, something was wrong. For years, physicists wrestled with the problem. Lord Rayleigh and Sir James Jeans attempted to refine classical models, but could not reconcile them with experiment. Wilhelm Wien proposed an empirical law that worked at higher frequencies, but failed at lower ones. The laboratory data were undeniable, but the theoretical framework of physics offered no solution. Many regarded the problem as a stubborn detail, an anomaly to be patched up someday, but not something that threatened the foundation of science. Planck, however, saw it differently. For him, the blackbody problem cut to the heart of thermodynamics and energy distribution. He believed it was not a small puzzle but a doorway to deeper understanding, and he devoted himself to it with relentless determination. Planck was not a man inclined to bold leaps or radical theories. His temperament was conservative, his instincts cautious. He revered the harmony of classical physics and long resisted any notion that it might fail. Yet, as the 19th century drew to a close, he found himself cornered by reality. Years of work had led him nowhere until finally, in a desperate effort to fit theory to experiment, he made a proposal so radical that it shook the foundations of science. On October 19, 1900, Planck presented a formula to the German Physical Society that perfectly matched the observed blackbody spectrum. The formula was simple in appearance, yet concealed within it a new principle. In deriving it, Planck had assumed that energy was not continuous, as everyone believed, but came in discrete packets. He called these packets quanta. The idea was almost unthinkable. Since Newton, scientists had treated energy as something that flowed smoothly, infinitely divisible. The notion that it could come only in little indivisible bundles contradicted centuries of belief. Planck himself did not fully grasp its implications. He admitted that he had adopted the assumption, as a purely formal assumption, to make the mathematics work, yet it was precisely this assumption that allowed him to resolve the ultraviolet catastrophe and bring theory into harmony with experiment. In that moment, the quantum was born, and with it, a new era of physics. The announcement did not make immediate waves. Many of Planck's colleagues saw his result as a clever trick, a mathematical convenience, not a fundamental truth about nature. Planck himself was uneasy, describing his discovery as an act of desperation. He hoped to someday reabsorb the quantum into classical theory, to reconcile it with continuity. Yet the genie was out of the bottle. What Planck had uncovered was not a temporary fix but a revolution, one that would soon sweep away the very idea of a deterministic, continuous universe. The radical nature of Planck's step is difficult to overstate. At the time, atoms themselves were not universally accepted, and the structure of matter was still under debate. To introduce discreteness into the very fabric of energy seemed almost heretical. Planck's equation, with its new constant now known as Planck's constant, became the cornerstone of the coming quantum theory. It suggested that the universe, at its most fundamental level, was granular, built from indivisible units of action. This was not merely a new equation, it was a new vision of reality. The early years after 1900 were marked by uncertainty. Planck continued to refine his theory, publishing further papers in which he tried to interpret the quantum hypothesis. Still, he hesitated to embrace its full meaning. To him, the assumption of energy quanta was a tool, not yet a physical reality, but younger physicists began to take it seriously. Albert Einstein in 1905 extended the quantum idea to light itself, proposing that light consisted of quanta, later called photons. With this step, the revolution deepened, and what Planck had reluctantly introduced became the seed of modern physics. But in 1900, none of this was visible. All that existed was a quiet professor in Berlin presenting an unorthodox solution to an obscure problem. He could not have imagined that his equation would eventually give rise to quantum mechanics, nuclear power, semiconductors, lasers, and the entire technological landscape of the modern world. His act of desperation would become one of the defining moments in the history of human thought. The atmosphere of that moment deserves to be remembered. Planck, standing before his peers at the German Physical Society, did not appear as a triumphant revolutionary. His voice was calm, his demeanor modest. He presented his law without fanfare, merely as a solution that seemed to work. The audience likely did not sense that they were witnessing the birth of a new era. For them, it was just another technical paper, one among many. Yet in retrospect, that evening in Berlin marked the beginning of the quantum century. Planck's personal reflections capture the tension of the time. He later recalled how reluctant he had been to abandon continuity, how he had resisted the idea of quanta until there was no other way forward. He described the discovery as a battle between faith and despair, a moment when his persistence in the face of failure forced him into a radical solution. It was not brilliance alone that created the quantum, but a willingness to confront failure honestly, to persist until even the most unthinkable step became inevitable. What makes this moment even more remarkable is that Planck did not set out to be a revolutionary. He was, in every sense, a conservative thinker, devoted to the old order of physics. Yet it was precisely his persistence and his refusal to abandon the problem that led him to break with tradition. The birth of quantum theory was not an act of rebellion but of necessity, and it came from a man who valued order above chaos. This paradox gives the story its drama, the reluctant revolutionary who transformed physics against his own instincts. As the 20th century unfolded, Planck's discovery gained momentum. Young physicists seized upon it, building models of the atom, exploring the photoelectric effect, and eventually developing quantum mechanics as a full-fledged theory. But the seed of all of this lay in that quiet presentation of 1900. The Blackbody problem, once a technical nuisance, had become the doorway to a new vision of the universe. Energy, once thought continuous, was now quantized. The smooth flow of classical physics had been broken into steps, and with it, the certainty of determinism began to crumble. The revolutionary birth of quantum theory was not greeted with fanfare, but with hesitation, doubt, and even resistance. Yet, as history has shown, revolutions in thought often begin not with trumpets, but with quiet voices, not with bold manifestos, but with reluctant admissions. Planck's quantum was just such a beginning. It emerged not from ambition, but from persistence, not from desire to destroy the old, but from a refusal to ignore reality. And in that act, the world of physics was transformed forever. The year 1900, remembered now as the moment when physics was reborn, did not feel revolutionary to those living through it. When Max Planck stood before his colleagues in Berlin and presented the formula that bore his name, there were no gasps of astonishment, no thunderous applause, no immediate recognition that the course of science had just changed. Instead, the event passed quietly, as though it were merely another technical presentation in the crowded calendar of the German Physical Society. Yet, history would come to see that day as the dividing line between two worlds, the classical world of Newton and Maxwell, and the quantum world of Planck and those who followed. Planck himself remained ambivalent in the weeks that followed. He was satisfied, almost relieved, that his formula finally fit the experimental data with uncanny precision. But he was uneasy about the assumptions he had made to reach it. The introduction of discrete energy quanta was a step so alien to the traditions of physics that he struggled to accept it as anything more than a mathematical device. He regarded it as a temporary tool, a stepping stone toward a deeper harmony that would eventually restore continuity. He was, by temperament and training, unwilling to abandon the ideals of classical physics. Yet even in his caution, he understood that something profound had taken place. In his private reflections, he described his discovery as if he had been forced by nature herself to make a leap he did not want to make, dragged reluctantly into a new landscape he could not yet see clearly. The scientific community, meanwhile, paid little immediate attention. Physics at the turn of the century was brimming with activity discoveries in radioactivity, the electron's identification by J.J. Thomson, and new developments in electromagnetism all vied for attention. Planck's paper on radiation was seen as a clever contribution, but hardly the centerpiece of a revolution. Many scientists assumed the odd assumption of energy quanta would soon be explained away by some refinement of classical laws. They were wrong, but it would take years before the depth of Planck's achievement became clear. What unfolded in the years after 1900 was the gradual realization that the quantum was not a trick, not a stopgap, but the key to an entirely new understanding of nature. Planck continued to refine his theory, publishing further papers in which he attempted to derive his formula from fundamental principles. Yet, despite his efforts, he could not escape the reality that discreteness was essential. The constant he introduced, Planck's constant, began to take on a life of its own, appearing again and again in contexts far removed from blackbody radiation. Slowly, the scientific world began to sense that this small number was a fundamental measure of the universe, a universal constant like the speed of light or the gravitational constant. In 1905, Albert Einstein delivered a bold interpretation of Planck's quantum hypothesis that gave it new power. In his explanation of the photoelectric effect, Einstein proposed that light itself was quantized, composed of individual packets of energy, what we now call photons. Where Planck had seen quanta as a property of energy exchange between matter and radiation, Einstein declared them to be real, physical constituents of light itself. This was a leap beyond what Planck himself had dared to suggest. At first, Planck was skeptical, uneasy with Einstein's radical interpretation, yet history would vindicate the younger physicist. The quantum had begun to spread, moving from a reluctant assumption into the very structure of physical reality. The revolutionary birth of quantum theory cannot be understood only as a mathematical step, it was also a philosophical shock. For centuries, Science had rested on the idea that nature was continuous, predictable, and deterministic. The quantum shattered this image. If energy came in packets, if radiation was quantized, then the smoothness of the world was an illusion. Beneath appearances lay a granularity, a world built not of continuous flows but of discrete steps. This realization did not come easily. It clashed with intuition, with centuries of tradition, and with the very identity of physics as the science of deterministic laws. Yet slowly, reluctantly, the community of scientists began to accept what Planck had uncovered. The years that followed his 1900 announcement revealed the full weight of the revolution. Niels Bohr built his atomic model on Planck's constant, explaining the spectral lines of hydrogen by assuming electrons could only occupy discrete orbits. Louis de Broglie extended the idea further, proposing that matter itself had quantum properties, that particles behaved like waves. Werner Heisenberg and Erwin Schrödinger gave mathematical form to the strange new world, building the structure of quantum mechanics. Each step traced its origin back to Planck's desperate hypothesis of 1900. Without that leap, the revolution could not have begun. And yet, through it all, Planck remained the reluctant founder. He accepted his role, but he never embraced the radical philosophical implications of the theory he had created. Where others saw a new universe of indeterminacy, Planck continued to search for deeper continuity. He recognized the necessity of quanta but struggled with the idea that the world was fundamentally discontinuous. His conservatism, paradoxically, made his discovery all the more powerful, for it was not born of rebellion or iconoclasm, but of persistence, of an almost reluctant honesty in the face of failure. He did not seek to overthrow the old order, but to save it. In the end, he built the foundation of a new one. The birth of quantum theory in 1900 was not marked by fireworks or revolutions in the streets. It was a quiet revolution, unfolding in the halls of academia, in journals and lectures, in debates among small circles of physicists. But its consequences were immense. It transformed not only physics but the modern world. From semiconductors to lasers, from nuclear energy to medical imaging, the quantum became the foundation of 20th century technology. The digital world of computers, smartphones, and the internet traces its lineage directly back to Planck's equation. The revolution that began in the quiet presentation of 1900 reshaped human civilization itself. Looking back, it is tempting to see inevitability in the story, to believe that if Planck had not introduced quanta, someone else would have. But history is rarely inevitable. It required the persistence of a man willing to labor for years on an obscure problem, willing to endure failure and frustration, willing to take a step he himself did not fully believe in. Without that persistence, the revolution might have been delayed for decades. The 20th century of physics and technology might have unfolded differently. Planck's act of desperation was not just a turning point for science, but one of those rare moments when the course of human history pivots on the choices of a single individual. There is a haunting quality to Planck's reflections on his discovery. He often described himself as having been compelled, almost against his will, to accept the quantum. He did not want to be a revolutionary, but he could not deny the truth that confronted him. In this sense, his story is a reminder of the deeper meaning of science, that it is not about comfort, nor about preserving tradition, but about following truth wherever it leads. Even when that truth defies intuition, even when it shatters centuries of belief, the scientist's duty is to persist. Planck embodied this duty. His persistence in the face of failure, his honesty in the face of contradiction, gave birth to the most profound transformation in our understanding of the universe. Today, more than a century later, we still live in the world created by that discovery. The quantum defines the structure of atoms, the chemistry of life, the stars above us, and the devices in our hands. It remains mysterious, strange, and often counterintuitive, but it is also the most accurate and powerful framework science has ever known. And it all began in 1900, when a cautious German physicist, seeking only to solve a stubborn problem, dared to suggest that energy was quantized. That moment, quiet and reluctant though it was, marked the birth of a new physics, a new vision of reality, and a new era for humanity. The revolutionary birth of quantum theory is remembered now as a turning point not just in science but in human thought. It showed that even when we believe we have reached the end of knowledge, nature can surprise us, forcing us to rethink everything. It showed that revolutions are not always loud or immediate, but can emerge from persistence, from patience, from the quiet voice of a man unwilling to give up. Max Planck did not set out to transform physics forever, but by following truth with relentless honesty, he did exactly that. At the dawn of the 20th century, classical physics stood as one of the greatest monuments of human thought. For over 2 centuries it had provided the foundation upon which scientists, engineers, and philosophers built their understanding of the natural world. Isaac Newton had given humanity laws of motion and gravity that explained everything from the fall of an apple to the orbit of planets. James Clerk Maxwell had unified electricity and magnetism into a majestic framework that not only described light as an electromagnetic wave, but also offered a vision of unity that inspired generations. Thermodynamics and statistical mechanics had woven together the behavior of gases, heat, and energy into precise mathematical forms. To the scholars of the late 19th century, physics seemed nearly complete, with only a few small clouds left to clear. Yet within those clouds lay storms that would tear apart the very foundations of classical thought. At the heart of this upheaval was Max Planck's daring, reluctant idea of quantized energy. To understand why Planck's hypothesis was so challenging, one must first appreciate how deeply the principle of continuity was ingrained in classical physics. In Newtonian mechanics, quantities like position, velocity, and energy varied smoothly. A moving body could have any speed, a system could absorb or emit energy in arbitrarily small amounts, and the mathematics of calculus allowed scientists to describe these continuous processes with precision. Maxwell's equations carried the same spirit. Electromagnetic waves could oscillate with any frequency and carry any energy, spreading across space in continuous patterns. Thermodynamics also rested on continuity, with temperature, pressure, and entropy treated as smooth, gradually changing variables. The entire edifice of 19th century physics was built on the conviction that nature flowed in an unbroken, deterministic continuum. It was precisely this conviction that Planck's quantum idea called into question. When he suggested that energy exchange between matter and radiation occurred in discrete packets, he introduced an element of granularity into a universe assumed to be smooth. Instead of energy being emitted or absorbed in infinitesimally small increments, Planck's formula required that it came in chunks proportional to frequency, with the proportionality constant h, Planck's constant. This was not merely a mathematical trick, it was a profound assault on the worldview of classical physics. If true, it implied that continuity was an illusion and that beneath the apparent smoothness of phenomena lay a deeper discreteness. For physicists who had grown up under the spell of Newton and Maxwell, this was almost unthinkable. The challenge was amplified by the success of classical physics in so many areas. The mechanics of planets, the engineering of machines, the propagation of light waves through space, all these had been explained with extraordinary accuracy. Why abandon a framework that worked so well? To many, Planck's quantum hypothesis seemed unnecessary, even absurd. It was, after all, introduced only to solve a particular puzzle, the shape of the Blackbody radiation spectrum. This spectrum, describing how an ideal object emits radiation at different wavelengths depending on temperature, had resisted all attempts at explanation. Classical theory produced results that diverged catastrophically from experimental data, predicting an infinite amount of energy emitted at short wavelengths, a failure known as the ultraviolet catastrophe. Planck's formula avoided the catastrophe, fitting the data with perfection. But the price of this success was the introduction of quantization, a step so radical that even Planck himself hesitated to accept its full implications. The scientific culture of the late 19th century made the resistance understandable. Physics was seen not merely as a body of laws but as a philosophy of nature. Determinism, continuity, and reductionism were not optional assumptions but articles of faith. To suggest that energy was not continuous was to threaten the very identity of physics. It implied that at a fundamental level, the universe operated according to principles beyond the reach of classical intuition. For many physicists, this was deeply unsettling. They had hoped to reduce all of nature to a set of universal, deterministic equations, leaving no room for discreteness or unpredictability. Planck's hypothesis was a crack in that dream, and through it the light of a new physics began to shine. Planck himself tried to minimize the challenge his idea posed. He presented quantization as a formal device, a convenient assumption to make the mathematics work, not as a literal feature of nature. He was, in many ways, the first skeptic of his own discovery. Yet the logic of his formula and the weight of experimental evidence forced him to confront the uncomfortable truth: the world seemed to obey quantization. His colleagues, too, resisted the full implications. Some treated Planck's work as a clever curiosity, not a foundational breakthrough. Others assumed it would eventually be reconciled with continuity, perhaps by some deeper refinement of classical laws. But as the years passed, the evidence only grew stronger, and the challenge to classical physics became undeniable. One of the clearest demonstrations of this challenge came with Einstein's work on the photoelectric effect in 1905. When light shone on certain metals, it ejected electrons, but classical wave theory could not explain the details of the phenomenon. According to Maxwell's equations, the energy of light was spread continuously across the wavefront, so increasing intensity should increase the energy imparted to electrons. Yet experiments showed that only the frequency of light mattered. Below a certain threshold, no electrons were emitted regardless of intensity, while above that threshold, electrons were ejected instantly. Einstein resolved this paradox by applying Planck's quantum idea directly to light, proposing that light itself consisted of discrete quanta, later called photons. This interpretation challenged not only continuity, but also the wave theory of light, one of the crowning achievements of 19th-century physics. If light was quantized, then the elegant wave picture was incomplete, perhaps even misleading. The implications were staggering. The challenge deepened as quantum ideas spread. Niels Bohr applied Planck's constant to the structure of atoms, suggesting that electrons could only occupy certain discrete orbits, with jumps between them corresponding to the emission or absorption of specific quanta of energy. This contradicted classical electrodynamics, which predicted that orbiting electrons should radiate continuously and spiral into the nucleus. Bohr's model worked, explaining the spectral lines of hydrogen with remarkable accuracy, but it did so by discarding the continuous assumptions of classical mechanics. Each success of the quantum idea was another blow to the old worldview, another demonstration that classical physics could no longer claim universal validity. For physicists trained in the classical tradition, these challenges were painful. They forced scientists to reconsider the very nature of reality. Was the universe continuous or discrete? Was determinism absolute, or did it give way to probabilistic laws at deeper levels? Planck's hypothesis, though simple in form, opened questions that cut to the heart of philosophy as well as science. The deterministic machine of Newton and the continuous waves of Maxwell could not fully capture the behavior of atoms, light, or radiation. Something more was needed, something radically new. And yet, despite the mounting evidence, acceptance did not come easily. Many of the greatest physicists of the early 20th century, including Planck himself, clung to classical ideals. They hoped the quantum would eventually be absorbed into a larger framework that restored continuity. Even as quantum mechanics developed in the 1920s under Heisenberg, Schrödinger, and Dirac, there remained deep resistance to abandoning determinism and continuity. Einstein famously rejected the probabilistic interpretation of quantum mechanics, insisting that God does not play dice. Planck, too, maintained a certain ambivalence, recognizing the necessity of quanta, but uneasy with their implications. The challenge his idea posed to classical physics was so profound that even its creator struggled to accept it fully. The conflict between quantization and classical continuity was more than a technical dispute. It was a cultural shift in the identity of physics itself. The elegance of continuous mathematics, the assurance of deterministic prediction, the harmony of unified laws, all these were undermined by the granularity Planck had introduced. To embrace the quantum was to accept a new vision of science, one in which probability replaced certainty, discreteness replaced smoothness, and mystery replaced clarity. It was a vision many resisted, but ultimately one they could not deny. Thus, Planck's quantum idea challenged classical physics, not only by solving a stubborn puzzle, but by shaking the very foundations upon which physics was built. It confronted scientists with the possibility that the universe was not the continuous machine they had imagined but something stranger, deeper, and more elusive. It forced them to rethink the meaning of science itself, to ask whether their equations described reality or only patterns of probability, whether their intuition could be trusted or whether it must yield to mathematics that defied common sense. The challenge was immense, but it was also the beginning of a revolution that would transform not only physics, but the modern world. The struggle between Planck's quantum hypothesis and classical physics did not unfold overnight. It stretched across decades, a slow erosion of certainty that left many of the greatest minds of science torn between loyalty to the old order and recognition of the new. What made this challenge so powerful was that it struck at the most fundamental assumptions about the universe, assumptions that had guided scientific thought since the age of Newton. To those raised in the classical tradition, continuity and determinism were not simply convenient descriptions of nature, they were its very essence. The notion that energy could be granular, that radiation could come in quanta, seemed at first to be not only unnecessary, but almost heretical. Yet experiment after experiment confirmed that classical physics could not explain the world of the very small. In the years immediately following Planck's 1900 presentation, physicists attempted to reconcile his results with classical frameworks. They tried to reinterpret his formula in terms of continuous waves, to find ways of smoothing over the discreteness. But each attempt failed. The ultraviolet catastrophe remained an unsolvable riddle within classical theory, and only Planck's assumption of quanta offered a way forward. Slowly, the recognition grew that quantization was not an accident of mathematics, but a reflection of reality. The fact that it worked so perfectly in describing blackbody radiation could not be ignored. Nature, it seemed, was whispering to scientists that their old assumptions were flawed. Einstein's bold use of quanta in 1905 gave further force to this whisper, turning it into something that could no longer be dismissed. By proposing that light itself behaved as if it were made of particles, Einstein forced the community to confront the possibility that the wave theory of light, one of the crowning achievements of Maxwell, was incomplete. The photoelectric effect revealed that energy could not be spread continuously across a wavefront. Instead, it arrived in packets, each sufficient to knock an electron free if its frequency was high enough. No matter how bright the light, if the frequency was below the threshold, nothing happened. This stark reality contradicted everything classical physics predicted. It was not merely an inconvenience, it was a violation of the very principles on which classical physics stood. The implications extended far beyond light. If radiation was quantized, then the interaction between matter and energy at every level needed to be re-examined. Atoms, once thought to be miniaturized solar systems governed by Newton's laws, could no longer be described as electrons circling smoothly around nuclei. Classical electrodynamics predicted that such electrons should continuously radiate energy and collapse into the nucleus, yet this did not occur. Bohr's model, inspired by Planck's constant, showed that electrons occupied discrete orbits and could leap between them, emitting or absorbing quanta of light. This was not a refinement of classical theory, but a complete rejection of its predictions. The atom itself, the basic unit of matter, revealed that continuity was an illusion. This was a profound shock. Classical physics had always promised that if one knew the initial conditions of a system precisely, its future could be predicted with certainty. This determinism was not just a scientific principle but a philosophical creed, embraced by thinkers who saw in it a vision of a universe governed entirely by rational laws. Planck's quantum hypothesis, and the developments it inspired, dismantled this vision. The discreteness of energy levels meant that even with perfect knowledge, certain outcomes could only be described in terms of probabilities. Later developments in quantum mechanics, with Heisenberg's uncertainty principle and Born's probabilistic interpretation, would make this explicit, but the seed was already planted in 1900 when Planck introduced his constant. The very idea of continuous predictability was under threat. The resistance to this challenge was fierce. Einstein himself, though he had used quanta to explain the photoelectric effect, remained deeply uncomfortable with the full implications of quantum mechanics. He believed that the universe must be governed by hidden variables, unseen factors that would restore determinism and continuity if only they were discovered. Planck, too, while accepting quantization as a necessary assumption, hoped it was only temporary. He never fully embraced the idea that the universe was fundamentally discontinuous. Even as quantum mechanics blossomed into a mature theory in the 1920s, both men clung to aspects of the old worldview. Their reluctance is a testament to just how radical the challenge was. For those who had grown up in the age of classical physics, abandoning continuity felt like abandoning the very soul of science. Yet the evidence was relentless. Spectroscopy revealed patterns of light emission that could only be explained by discrete energy levels. Experiments with electrons confirmed wave-particle duality, showing that particles could behave like waves and waves like particles, a concept unimaginable within classical frameworks. The double-slit experiment, in particular, became an icon of the quantum challenge. A single electron, when sent through two slits, produced an interference pattern as if it were a wave, but when measured, it appeared as a localized particle. Classical physics could not account for such behavior. It was as if reality itself defied the categories that Newton and Maxwell had established. As the quantum idea spread, its challenge to classical physics became not just scientific but philosophical. What did it mean for a theory to describe reality? If energy was quantized, if probability replaced certainty, could science still claim to offer a complete description of nature? Some physicists embraced the change, seeing in quantum mechanics a deeper and more flexible framework. Others resisted, uncomfortable with the abandonment of determinism. The debates were intense, sometimes bitter, but they underscored the depth of the challenge. Planck's modest constant, introduced reluctantly, had become the wedge that split physics into old and new. The true magnitude of this challenge can only be appreciated when we consider the cultural and intellectual context of the time. The 19th century was an age of confidence in science, an era when many believed that physics was nearly complete. Lord Kelvin famously declared that only two small clouds remained on the horizon, and those clouds would soon be cleared away. One of those clouds was Blackbody radiation, the very problem Planck addressed. No one could have imagined that the solution would not be a minor correction, but a complete overthrow of classical assumptions. Instead of clearing the sky, Planck's hypothesis revealed an entirely new landscape beyond the horizon, one that required abandoning much of what had seemed certain. The irony is that Planck himself was no revolutionary in spirit. He was a man of tradition, deeply respectful of classical physics, reluctant to embrace radical change. His quantum idea was born of desperation, not rebellion, yet it was precisely this reluctance that made his discovery so powerful. Because he had not sought to overthrow classical physics, his challenge could not be dismissed as reckless speculation. It was the result of painstaking work grounded in experimental reality, presented by a man who valued continuity above all. That such a man could be driven to introduce discreteness gave the idea credibility it might otherwise have lacked. Over time, the challenge of the quantum reshaped not only physics but the modern world. The technologies that define contemporary life, semiconductors, lasers, nuclear energy, medical imaging, quantum computers, all depend on the rejection of classical continuity. Each device is a reminder that Planck's hypothesis, once resisted and minimized, has become the bedrock of reality. The old vision of a continuous, deterministic universe has given way to a world where probability and discreteness are fundamental. This transformation is perhaps the most profound intellectual shift in the history of science. And yet, the echoes of the challenge remain. Even today, physicists grapple with the implications of quantization. Questions about the nature of reality, the role of probability, and the meaning of measurement continue to spark debate. The quantum revolution is not over, it is ongoing. But its origins lie in the moment when Planck dared to suggest that energy came in quanta, challenging the continuity that had ruled science for centuries. That act, reluctant and cautious though it was, marked the beginning of a new era. Thus, the challenge of Planck's quantum idea to classical physics was not just a matter of correcting equations. It was the dismantling of an entire worldview. It forced scientists to abandon the comforting certainty of determinism, to accept the granularity of energy, to embrace a universe more mysterious than they had ever imagined. It was in every sense a revolution, and like all revolutions it began with a single step, a step taken by Max Planck in 1900, a step that he himself did not fully believe in, but one that changed the course of science and the destiny of humanity. When Max Planck introduced his constant in the year 1900, he could not have known that this small symbol, denoted by the letter h, would come to occupy a central place in the language of physics. At first, it was little more than a mathematical tool, a proportionality factor that allowed him to link the frequency of radiation to discrete packets of energy. Yet as the years passed, it became clear that Planck's constant was far more than a convenient number. It was a new universal constant, as fundamental to the fabric of reality as the speed of light or the strength of gravity. In its compact form, it carried within it the seeds of a revolution, defining the scale at which the quantum world revealed itself and setting limits on what could be known about nature. The magnitude of h is extraordinarily small, about 6.626 tonjoule-seconds. To the human eye, to the scale of everyday life, it seems almost negligible. But this tiny number marks the boundary between the classical and quantum domains. At the level of planets, machines, and visible objects, h is so small that its effects vanish into insignificance, and the continuous predictions of classical physics remain valid. But at the scale of atoms, electrons, and photons, Planck's constant dictates the rules. It is there that continuity dissolves and discreteness takes over. It is there that energy levels come in steps, that light arrives in quanta, that probabilities replace certainties. Planck's constant is, in this sense, the fingerprint of the quantum realm, the number that tells us how the universe truly operates beneath the surface. One of the first signs of its universal power came from Niels Bohr's atomic model. By using Planck's constant to define the allowed orbits of electrons in the hydrogen atom, Bohr was able to explain the spectral lines of hydrogen with striking accuracy. The colors of light emitted when electrons jumped between these orbits corresponded precisely to the quantized energy levels determined by h. Suddenly, what had seemed an arbitrary feature of atomic spectra was revealed as a direct consequence of the quantum constant. It became clear that h was not restricted to radiation problems, but was woven into the structure of matter itself. Every atom in the universe carried within it the imprint of Planck's discovery. As quantum theory developed further, Planck's constant appeared in equation after equation, always signaling the presence of quantization. In Heisenberg's formulation of quantum mechanics, h defined the uncertainty principle, setting a fundamental limit on the precision with which position and momentum could be known simultaneously. In Schrödinger's wave mechanics, it determined the wavelength of matter waves, dictating the dual behavior of particles as both localized entities and spread-out waves. In Dirac's work, it linked quantum theory with relativity, shaping the equations that predicted antimatter. In each case, H was not an afterthought but the key, the silent guide reminding physicists that the world of the very small obeyed rules unlike anything classical physics could provide. What makes Planck's constant so profound is its universality. It does not belong to one branch of physics or another, but appears wherever the quantum world is described. It governs the photons that carry light across the cosmos, the electrons that form chemical bonds, the nuclear processes that power stars, and the superconducting circuits that drive quantum computers. It is present in the semiconductors that underlie modern electronics, in the lasers that guide surgical instruments, in the magnetic resonance imaging that peers inside the human body. It is, quite literally, the number on which modern civilization rests, even if most people never hear its name. Beyond technology, H has a deeper meaning as a measure of reality's granularity. Just as the speed of light sets the ultimate limit on motion, and the gravitational constant shapes the structure of space and time, Planck's constant defines the minimum unit of action, the smallest indivisible scale at which processes in nature occur. It tells us that the universe is not infinitely divisible but built upon discrete foundations. For centuries, philosophers had debated whether matter and energy were continuous or atomic in nature. With Planck's constant, physics answered the question. At the deepest level, discreteness reigns. Even the definition of fundamental units of measurement has been reshaped by H. In 2019, the kilogram itself, the base unit of mass in the International System of Units, was redefined in terms of Planck's constant. This decision reflected the recognition that H is not a man-made construct, but a universal constant, unchanging, timeless, and woven into the structure of the cosmos. By anchoring our system of measurement to Planck's constant, humanity acknowledged that this small number discovered in a moment of desperation more than a century ago is one of the bedrocks of nature. Yet perhaps the most remarkable aspect of Planck's constant is not only its scientific utility, but its philosophical weight. It reminds us that the universe is stranger than our intuition suggests, that beneath the smooth flow of everyday experience lies a world of jumps, quanta, and uncertainties. It challenges our sense of determinism, our longing for certainty, and replaces them with probability, discreteness, and limits. It is a constant that humbles human understanding, showing us that even the most brilliant classical theories capture only an approximation of reality. Planck himself, though he introduced H reluctantly, lived to see its universal significance. He recognized that it was not merely a fitting parameter, but a window into the foundations of nature. While he never fully embraced the philosophical upheavals that quantum mechanics would bring, he accepted that his constant had opened a new era. And so today, more than a century later, when physicists write their equations or engineers design their quantum devices, they invoke Planck's constant as naturally as they invoke Newton's laws or Einstein's relativity. It is the quiet signature of the quantum world, the constant that transformed physics forever. When the 19th century was drawing to a close, physics appeared nearly complete. Newton's laws of motion, Maxwell's equations of electromagnetism, and the principles of thermodynamics formed a grand structure that seemed to describe the universe in its entirety. Many believed that only minor refinements were left to be made, polishing details rather than overturning foundations. Yet, beneath this calm surface, certain problems lingered. Chief among them was the mystery of blackbody radiation, a problem that resisted every classical attempt at explanation. It was Max Planck's daring solution to this puzzle that ignited a revolution, in introducing the idea that energy came not in a smooth flow but in discrete packets. Planck unknowingly cracked the foundations of classical certainty, and lit the first spark of what would become quantum mechanics. The consequences of this step were far greater than even Planck imagined. His constant h was at first a mathematical tool, a way to reconcile theory with experiment. But soon it became clear that the quantization of energy was not a mathematical trick but a real feature of nature. The idea was radical. Energy itself was granular, photons were not waves in the old sense but quantized bundles, and matter was not governed by strict determinism but by probability. This realization opened the door to the work of Einstein, who applied the quantum idea to explain the photoelectric effect, revealing that light behaved both as a wave and a particle. This duality shook the very philosophy of science, dissolving the boundaries between categories that had seemed absolute for centuries. As the early decades of the 20th century unfolded, Planck's quantum hypothesis grew into a full-fledged framework. Bohr constructed his atomic model using Planck's constant to explain the stability of atoms and their spectral lines. Heisenberg, Schrödinger, and Dirac developed new mathematical languages, matrix mechanics, wave mechanics, and relativistic quantum theory, that described the strange behavior of particles with astonishing accuracy. Each of these breakthroughs traced its origin back to Planck's bold step in 1900. Without quantization, the entire edifice of quantum mechanics would never have arisen. Thus, Planck did not merely solve a thermal radiation puzzle. He opened a gateway into a new universe of ideas, a universe where uncertainty, discreteness, and duality replaced the comfort of continuity and determinism. The impact of this new science was profound, reaching far beyond laboratories and lecture halls. In chemistry, quantum mechanics explained why atoms form the bonds they do, why molecules take their shapes, why elements behave in predictable patterns on the periodic table. The mysterious principles of valency and reactivity, once empirical rules, found their explanation in the quantum structure of electron shells. In solid-state physics, quantum theory unveiled the secrets of semiconductors, paving the way for transistors, computers, and modern electronics. In astrophysics, it revealed the processes by which stars shine, how nuclear fusion operates, and why matter holds together in the extreme conditions of white dwarfs and neutron stars. Each triumph reaffirmed that Planck's modest idea was not a narrow fix, but the seed of a paradigm shift. Even more striking was the philosophical impact. Quantum mechanics did not simply refine classical ideas, it shattered them. The determinism of Newtonian physics, where the present state of the universe dictated the future with perfect certainty, was replaced by the uncertainty principle, where probabilities defined outcomes and measurement itself influenced reality. Einstein, though he contributed to quantum theory, resisted its implications, declaring that God does not play dice. Yet the experiments proved otherwise. Electrons interfered like waves and collapsed like particles. Particles tunneled through barriers they should not pass, and entanglement linked distant particles in ways that defied common sense. This was not an error in theory, but a new truth of nature, a truth first signaled by Planck's constant. In the practical world, the birth of quantum mechanics reshaped human civilization. The discovery of lasers, transistors, superconductors, and magnetic resonance imaging all stemmed from the quantum revolution. Entire industries rose from quantum principles: telecommunications, information technology, nuclear power, and more recently, quantum computing and quantum cryptography. These technologies are not side effects but direct descendants of the moment Planck introduced energy quanta. The thread that runs from Planck's Blackbody curve to the smartphone in a pocket is unbroken, a testament to the transformative power of one scientific insight. But beyond applications lies a more enduring legacy. Quantum mechanics changed how humanity sees itself in the universe. It revealed that certainty is an illusion, that reality is not a fixed clockwork, but a tapestry woven from chance and probability. It showed that matter and energy are not separate categories but manifestations of deeper quantum fields. It challenged intuition and forced philosophy, mathematics, and science to evolve. In this way, the birth of quantum mechanics was not merely a chapter in physics, but a turning point in intellectual history, one that redefined knowledge itself. Planck, the reluctant father of quantum theory, once admitted that his constant was introduced as an act of desperation. Yet out of that desperation came a new foundation for science, one that continues to shape the 21st century as deeply as it shaped the 20th. From the structure of DNA to the behavior of black holes, from the circuitry of microchips to the exploration of parallel universes, quantum mechanics extends its reach endlessly. It is the theory that unifies the microscopic with the cosmic, the theory that began when a quiet German physicist dared to imagine that nature's energy comes not in a continuous stream, but in indivisible quanta. That moment was not just the birth of a new theory, it was the birth of modern physics itself. When Max Planck first introduced his strange idea of quantized energy, he did not intend to overturn the entire structure of physics. He thought of it as a temporary assumption, a clever mathematical tool to solve an intractable puzzle. Yet once released into the scientific world, the idea could not be contained. Other minds seized upon it, expanded it, and gave it interpretations far beyond what Planck had imagined. Among these minds, none was more influential than Albert Einstein. In 1905, just 5 years after Planck's Blackbody breakthrough, Einstein applied the quantum hypothesis to explain the photoelectric effect. He argued that light itself was quantized, that it came in discrete packets of energy called photons, and that these photons could liberate electrons from metal surfaces in ways classical wave theory could never predict. This proposal was audacious, for it implied that light was not simply a wave, as Maxwell's equations suggested, but also a particle-like entity. Einstein's idea, born from Planck's constant, became one of the key milestones in the birth of quantum physics and eventually earned him the Nobel Prize in 1921. Planck himself was initially uneasy about Einstein's bold interpretation. He admired Einstein's brilliance and defended his relativity theory when others doubted it. Yet he hesitated to embrace the radical notion of light quanta. For Planck, the quantization of radiation was at first a formal device, not a literal description of reality. He continued to believe that electromagnetic waves were fundamentally continuous, and he resisted the full implications of Einstein's photons. Still, he encouraged open discussion and gave space to ideas that challenged his own instincts. In this way, Planck's influence was not limited to equations, but extended into the culture of science itself. He exemplified the intellectual honesty to accept results even when they unsettled his worldview, and this attitude created fertile ground for Einstein and others to explore. Einstein was not the only one transformed by Planck's constant. Niels Bohr built his model of the atom upon it, showing how electrons occupied quantized orbits and explaining the hydrogen spectrum with extraordinary precision. Werner Heisenberg, inspired by this same principle, developed matrix mechanics, which became the first full mathematical formulation of quantum mechanics. Erwin Schrödinger soon followed with wave mechanics, offering a different but equivalent vision of the quantum world, one that revealed electrons behaving like standing waves around atomic nuclei. Paul Dirac later combined quantum mechanics with relativity, predicting antimatter. In each of these leaps, Planck's constant was the silent cornerstone, guiding theory after theory, equation after equation. Without H, these revolutions would have had no foundation. The influence also extended beyond the circle of theoreticians. Experimental physicists began to confirm the predictions of the quantum world, often in ways that astonished even the theorists themselves. Spectroscopic measurements confirmed Bohr's quantized orbits, while electron diffraction experiments revealed the wave nature of matter that Schrödinger had described. In all these experimental triumphs, Planck's constant appeared as the numerical bridge between theory and reality, the marker of where classical physics broke down and quantum mechanics began. It became the physicist's compass, pointing to the domain where new discoveries awaited. Yet Planck's influence was not confined to physics alone. The philosophical implications of his discovery reverberated through the wider intellectual community. For centuries, Determinism had been the bedrock of scientific thought. Newton's mechanics had suggested a clockwork universe, one in which the future could be calculated with perfect certainty if the present were known. But Planck's constant implied a new kind of limit, one that Heisenberg later formalized as the uncertainty principle. The precision of knowledge was no longer infinite. Nature had boundaries, not just of speed or energy, but of knowability itself. Philosophers, mathematicians, and even theologians wrestled with these implications. Reality seemed less like a machine and more like a tapestry woven from chance, probability, and hidden patterns. Planck himself, ever cautious, did not fully embrace this philosophical upheaval. He remained convinced that beneath the probabilistic language of quantum theory lay a deeper order, a reality that classical intuition might one day recover. He respected Einstein's skepticism toward quantum mechanics, even as the younger generation accepted it with enthusiasm. But regardless of his personal reservations, Planck could not stop what he had begun. His constant had escaped the confines of his original model and become the emblem of an entirely new worldview. In the wider scientific community, Planck was also a leader of extraordinary influence. As a respected figure in German academia, he held positions of authority that allowed him to support young scientists and defend bold new ideas. When Einstein's theory of relativity was met with suspicion and resistance, Planck stood among its earliest defenders, recognizing its elegance and consistency. He used his reputation to shield Einstein from critics and to ensure that revolutionary ideas were given a fair hearing. This willingness to support new thinking reflected Planck's recognition that science advances not through comfort, but through challenge, not by clinging to tradition, but by daring to question it. The ripple effects of Planck's constant eventually extended into the practical world. As quantum mechanics matured, it gave rise to entire industries: electronics, lasers, nuclear energy, and quantum information technology. Each advance traced its lineage back to Planck's discovery, and each scientist who built upon it carried his influence forward. Even today, as physicists explore quantum computing, entanglement, and the unification of forces, Planck's constant remains at the center, a reminder of where it all began. His influence is not frozen in history, but continues to shape the future of science and technology. What makes this influence remarkable is its dual nature. On one hand, Planck transformed physics through a single constant, a number that defined the boundary between classical and quantum worlds. On the other hand, he transformed the scientific community by modeling intellectual courage, humility, and openness to the unexpected. He showed that even a reluctant revolutionary can ignite a movement that reshapes the foundations of knowledge, and through his encouragement of Einstein, Bohr, Heisenberg, Schrödinger, and countless others, he ensured that the quantum revolution was not the work of one man, but a collective effort inspired by his breakthrough. Thus, Planck's influence cannot be measured only in equations or discoveries. It must also be seen in the way science itself evolved, in the courage to abandon certainty, in the willingness to embrace paradox, and in the readiness to follow truth wherever it led. His constant H became the symbol of a new physics, but his legacy as a mentor, defender, and catalyst became the symbol of a new scientific culture. And so, from Einstein's photons to Bohr's atoms, from Heisenberg's uncertainty to the technologies of the modern age, the influence of Max Planck endures, echoing across time, as the spark that ignited a new way of seeing the universe. When Max Planck stood before the German Physical Society in December 1900 to present his findings on blackbody radiation, he could not have foreseen how deeply his ideas would transform the future. What began as a desperate mathematical solution to a stubborn problem became the seed of a revolution, and more than a century later, his influence continues to shape the foundations of science and the fabric of technology. Planck's constant, that small number representing the quantization of energy, has become one of the cornerstones of modern physics. Standing alongside the speed of light and Newton's gravitational constant as a fundamental descriptor of reality, His legacy is not confined to textbooks or laboratories. It lives in the devices we use, the theories that guide our understanding of the universe, and the philosophical frameworks that define how humanity perceives existence. Today, every branch of physics bears the imprint of Planck's discovery. In particle physics, the behavior of quarks and leptons, the interactions of fundamental forces, and the existence of Higgs bosons are all described within frameworks that depend upon quantization. In cosmology, the very origin of the universe is explored through the lens of quantum fluctuations, Planck, scale energies, and the birth of space and time themselves. The Big Bang theory and models of cosmic inflation all rest on quantum principles that trace their ancestry back to Planck's first constant. Even the search for a theory of quantum gravity, the elusive union of Einstein's relativity with quantum mechanics, is ultimately a search to understand reality at the scale where Planck's constant, the speed of light, and gravity intertwine. The term, Planck scale, itself has become synonymous with the deepest mysteries of the cosmos. It refers to distances and times so small that our current theories collapse, where space and time are thought to lose their smoothness and become foamy and discrete. At this unimaginably tiny level, around 10 by meters, the universe as we know it ceases to exist in familiar terms, and a new as yet unknown physics must take over. That scale carries his name because it was his constant that first pointed toward the existence of such a fundamental boundary. In this way, Planck's legacy stretches not only across what we know, but also into the vast frontier of what we still seek to discover. The influence is not confined to theory alone. Planck's constant underpins the technologies that define modern civilization. The lasers used in medicine and communications, the semiconductors that power computers and smartphones, the magnetic resonance imaging machines that peer inside the human body, and the nuclear technologies that provide energy. All of these rely on principles of quantum mechanics born from Planck's idea. Without quantization, there would be no transistors, no internet, no satellites navigating with atomic clocks, no solar panels converting photons into electricity. The digital revolution itself is a direct descendant of Planck's insight. Even more striking, the emerging industries of the 21st century, quantum computing, quantum cryptography, quantum teleportation, stand upon the same foundation, carrying his influence into a future he could never have imagined. Planck's legacy also endures in the standards by which humanity measures the world. For centuries, the kilogram was defined by a physical artifact, a small platinum, iridium cylinder stored in France. But in 2019, the definition of the kilogram was redefined in terms of Planck's constant, fixing its value forever as part of the international system of units. This change symbolized more than a technical adjustment. It represented a recognition that Planck's discovery was not merely a theoretical tool, but a universal truth. The very act of measurement, the way humanity defines mass itself, now rests upon the constant he introduced more than a century ago. Beyond equations and instruments, Planck's enduring legacy is also philosophical. He reminded humanity that reality is not always aligned with intuition, that nature often reveals truths that defy common sense. His constant became the first crack in the facade of classical certainty, showing that energy is discrete, knowledge is limited, and probability is fundamental. This shift did more than change physics, it reshaped the way humans think about existence. Determinism gave way to uncertainty. Absolutes gave way to probabilities, and the universe revealed itself to be stranger and more mysterious than ever imagined. This philosophical shift influenced not only scientists but artists, writers, and thinkers who drew inspiration from the quantum world to explore themes of chance, uncertainty, and the hidden structures of reality. Planck's personal legacy also endures in the institutions and communities he helped build. He was not only a theorist but a mentor, a defender of bold ideas, and a leader in the scientific world. He nurtured young physicists, supported Einstein when relativity was under attack, and maintained his integrity through the turbulence of war and political upheaval. His name now adorns the Max Planck Society, one of the world's leading research organizations, supporting thousands of scientists across disciplines, carrying forward his spirit of inquiry. Through these institutions, his legacy is not frozen in history, but alive in the ongoing pursuit of knowledge. Even as physics continues to advance, Planck's constant remains a reminder of humility. It tells scientists that there are limits to what can be known with certainty, that reality may operate according to rules that human logic struggles to grasp. It whispers that there are boundaries to space and time, beyond which our theories cannot yet reach, and it inspires new generations to push those boundaries, to seek a deeper understanding of the universe at its most fundamental level. In this way, Planck's enduring legacy is not only in what he gave to science, but in the questions he left behind. More than 100 years after that December evening in Berlin, Planck's discovery continues to ripple outward. It links the microworld of electrons to the vastness of galaxies, the devices in our pockets to the origins of the cosmos, the certainty of mathematics to the uncertainty of reality. It stands as proof that a single insight, born of persistence and imagination, can transform not only a field of study, but the entire trajectory of human civilization. Max Planck may have entered the problem reluctantly, seeking only to solve a technical puzzle, but in doing so, he opened the quantum age. His constant endures as one of the great symbols of science, his legacy etched not just in equations, but in the very structure of the universe itself.